Hello and welcome to the second lecture in the algorithmic problem solving course. So today I will be talking about the data structures and a little bit about the greedy and dynamic programming just to give you a sense of what it is and so that you can solve the second week of problems. So at the first lecture, I showed you this table, which provides an overview of the kind of computational complexity which is required to solve the different problems. So actually, I think this table is probably one of the most important parts of this course because to solve the problems in this course, you can assume that you have 100 million operations. And then, of course, the question is, depending on how large the problem is, what kind of computational complexity can you actually get away with? And that's the purpose of this table. So today we will basically be talking about algorithms and methods towards the lower end of this table. That means that they're really fast. So basically linear or logarithmic or n log n complexity. Of course, the dynamic programming may be a bit more time consuming. So before we get started, it's very important that you get to know the basic data structures and that you get efficient and quick in using this when solving problems throughout this course. So in your favorite programming language, there is most likely a number of linear data structures, such as pair, tuple, arrays, vectors, bit sets, stacks, queues, dequeues, and so on. And for all of these, it means that they're linear, meaning that you can extend them, but you cannot, you can grow them if you need. And then there is linked list data structure. So basically the linked list, which is actually, it has some very specific use cases, but it's very rarely used in practice. However, we will see one example of that. And then there are a number of tree-like data structures. So here we have basically everything where you need to be able to sort things. So like priority queues, heaps, and sets, but also maps, so that you can map one key to some data value, and also unordered maps, which are usually implemented as some form of hash table. So in parentheses, you can see the names of these data sets in C++ or Java. So basically all of these data structures are available in these two languages in one form or another. And the main message here is that basically every program you write in this course will use one or more of these. So really get to know how to use them quickly and effectively. Just to give you some examples of how these can be used. So there is a UVA problem called 10,107, which basically is about computing the median of n integers. So it means that you need to always be able to ask what is the current median in your data set. So there are, of course, a number of different ways of solving this. For example, you can have a vector, and then you need to sort this vector, which is an n log n algorithm. And if it's sorted, you can just take out the middle element or take the average of the two middle elements if it's an even length list, and then you can compute the median. If you have a linked list, then you can basically keep it sorted, which means that you can always insert in the right place. So you basically need to do a linear search to find the place where to insert, and then you can grow the list. This is basically a version of insertion sort, meaning that this is basically an n log n, n quadratic algorithm. And then we can use, for example, a heap or some other balanced tree, which is always try to keep the tree with the lowest possible height. That's why it's called balanced. And where the elements are always sorted. And here, this is actually similar to the linked list, but with the difference that you using a binary search to find out where to add your element. So basically, this is an n log n method to achieve this problem. So these are some. So this is a good problem to practice to solve using these basic data structures. Another interesting practice example is problem number 902, where you're basically required to find the most frequent string of length n in a text. So here, what you want to do is to basically map each substring to a number, so you can keep track of how many times each string has been seen. And then, of course, you need to find all the strings of a certain length, so that you can be doing then in order t log tn, where the t is the length of the text. So this is another simple problem where you can practice using these basic data structures. Okay, so after that quick introduction to some of the most important basic data structures, we will now see some examples of a greedy algorithm and dynamic programming. So the first important problem that we will cover is the interval cover problem. So here you're given a goal interval, S, F, and a set of intervals, and we know that the union of all the smaller intervals are sufficient to cover the goal interval. What we're now interested in is finding the smallest subset, so with the fewest number of sub-intervals that is required to actually cover all of the goal interval. And this is then an example of a greedy algorithm. A greedy algorithm is an algorithm where a local optimal choice will lead to a global optimal solution, which means that we basically have to do a linear pass through some data structure, and in each step we can greedily or locally optimally make a choice, and we know that we never need to rethink this choice, but that this will be sufficient to actually find a globally optimal solution. So in the interval cover example, what we need to do is to initialize so that the starting point of our first interval is S, the starting point of the goal interval. And then as long as our kind of current point is smaller than the end point of our goal interval, we're trying to find the interval among the possible subintervals with the latest end time, which covers this start time. So basically what we're trying to do is to find an interval which covers the current point and where the end time is as late as possible. So, and then when we have found this, we then update the next starting point to the time point where this interval ends. And then we just repeat that, and that is guaranteed to give us the optimal interval cover. And of course, now you should think about, why is this greedy algorithm optimal? Usually one good way of thinking here is that assume that a choice could lead to a suboptimal alternative, and then kind of disprove this. Then you can do it by negation, for example. That's one way of doing it. And another thing is, how can we improve this method, which is currently quadratic, into an n log n algorithm? And a hint here is that it's about ordering, and usually that by ordering your elements in a clever way, then in almost every case it's possible to get these greedy methods to actually be solvable in n log n or faster time. Okay, so that was one example. The second example is one example of a dynamic programming. So here we're interested in a famous problem called the knapsack problem. And here we're given a backpack with a capacity C, and then we have a set of possible objects where each object has a weight and a value. And now we're interested in finding the subset with the highest value that you can actually fit within your backpack, meaning that the sum of the weights is below the total capacity of your knapsack, but the sum of the values is as high as it can be. And this is an example of a problem where order matters, which means that there is no greedy choice, but rather we basically have to try many different combinations. So a brute force solution to this would be to test every subset of the possible objects. For each possible subset, if the weight is below the capacity, then we sum up the values, and that is the value of that subset. If the capacity is, if it goes above the capacity, then of course the value is basically 0 or -1 or something like that. And then you just have to find that subset which is has the highest value. So then of course we know that if we have a set of size n, there are 2 to the power of n possible subsets. So of course then this would be an exponential method. So the question is, can we do better than this? And we can. If we fix the capacity, then we can do better. So here, and the way we do this is that we define smaller subproblems so that if we can solve the smaller subproblems, we can then put together a solution to the larger problem. And here the subproblem is, should I put the item with index I in knapsack if I carry W weight? So basically, how much capacity do I have? Depending on how much capacity you have left, determining whether a particular item should be included or not into your knapsack. So this means that our decision state, so basically our state is the index I and the current weight W. And then what we can do is that we can basically compute each subproblem once and store them in a table. I usually call them DP or M for memory, so that in this case it will be a two-dimensional array. The number of objects, which is the range over which I will vary, and of course the max weight, depending on how much W can be. And then we just have to fill in this matrix, starting basically with either 0 weight or only one capacity left. And then we just try for each object what is the value we would get if we include this object, and what is the value we would get if we don't include this object. And then we take the maximum of those, and that is the value of each of these cells. And this knapsack problem actually generalizes many well-known optimization problems. And I would say in general, dynamic programming is a technique which allows you to solve a large range of different optimization problems. My personal approach to this is to formulate a recursive definition of what we want to achieve. So in this case, it's given the state IW, it means that you can then, for example, if you include the object in your knapsack, then you need to increase the weight with the weight of this particular object. But of course, you also increase the value of that with the value of that. So that is then, so then you get a new state, and then you can look up what is the value of that, and you sum these two up. Or you can decide to not include the object, and then the weight is not increased, and you just increase the index I by 1, and then you look up what is the value in that particular state, and then you take the maximum of these two. That is the value for this particular decision state. So that is one important type of problem. And then one interesting data structure is called the disjoint set, which is explicitly being used to keep track of sets of sets. It's also called the union find method. So a disjoint set is a data structure for storing a set of disjoint sets, which is very efficient, both to find and to merge two sets. So basically, for example, assume that we have all the numbers between 1 and n, and now we want to keep track of these objects belonging to different sets. So we know that each element can only belong to one set, but which set it belongs to can vary over time, and so we can have many of these sets. And that's the type of data structure we have here. So disjoint sets are represented by a forest of trees. I'm sure you're all familiar with trees. So a tree has a root, and then it has a number of elements below the root or above the root, depending on how you turn your tree. And then a forest is just a set of such trees. So in the disjoint set, each tree is represented by this root element. So that's the representation of this set. Yes. And now I realize that here I usually draw some images of how these data structures actually work. I actually would recommend that you look up how this disjoint sets actually work. But basically, the idea is that you keep track of these representative elements. And when you add an element, or sorry, when you merge two sets, take the union of these two sets, you add a pointer from the representative element of one tree, the one set, to the representative element of the second tree. And by adding that link, you basically have now extended the tree. And that means that now this element, or sorry, this new tree represents the union of these two original trees. And then there is a number of techniques that one can use to improve the performance. For example, path compression, which is basically when you look up at an element, you can remove all the intermediary steps in the tree so that you only have the representative element, the root element, and then you put a direct link to the particular element that you want to find. And the main use, or one of the main usages of this union find data structure is to find connected components in an undirected graph. So basically, you have the set of all nodes, and now you want to find out which of these nodes are connected. So basically, if two nodes have an edge, then you take the union of the two sets that these two nodes belong to. And then you just continue that for every edge. And then at the end, you will have this forest of sets where each set is a connected component. Or to find the minimum spanning tree. So the minimum spanning tree is that given a graph, so we have a set of nodes connected by edges. Now we want to find the minimum number of edges, or the minimum total length of edges, which connects every node in this original graph. So basically, we want to find a tree which spans, that is, connects all the nodes in the graph, but with the fewest number of edges, or the shortest total length of edges. And to do that, you basically do the same approach as we did with the connected components. But here it's more, you take the shortest edge. If the shortest edge connects to previously unconnected components, then you add it. Otherwise, if this edge is within a connected component, then we just discard it. So then we go through all the edges one by one, sorted by length, and at the end we will have the minimum spanning tree. And then there is an exercise called the almost union find, and then you extend this basic union find data structure with delete and move, so that you should be able to remove nodes, and you should be able to move nodes, so individual nodes, not the full set, from one set to another. And actually, this is also a problem in this week's IMPA contest. So added bonus there. Then we come to another very important basic data structure, which is the Fenwick tree, named after Peter Fenwick. And this is an efficient data structure for computing range sum queries and updates, meaning that we basically need to sum up a set of elements, and where we need to update this data structure efficiently. So we can actually do both of those in logarithmic time. I mean, a naive implementation would be linear. So what we're talking about here is very efficient algorithms. So in this data structure, you only store the actual sums. So basically, you store the number of the frequency up to a certain point, not the original values, but you can always regain these original values by taking the difference between, for example, the position I and I plus 1, and then you get the difference. That's the particular value there. And the general idea here is that each integer can be represented as sum of powers of 2. So in the same way, cumulative frequency can be represented as a sum of sets of subfrequencies. So this means that we represent these sets as successions of a non-overlapping frequencies. So, I mean, I will not go through the detail. It's much easier to read. On the course webpage, there is a link both to a set of slides from Stephen Halim, and there's also a link to a visualization which allows you to play around with these Fenwick trees and get a better understanding of how they work. So here, if the data is static, then we could, of course, have been computing this in linear time. So basically, given this input values, we could then just with one pass through the data, compute this range sum. But now the question here is, of course, if we want to update it. And when we need to update it, then that method will not work. So rather, we will need to build a tree, which is also called bit index tree. So basically, the idea here is that we store element I. It actually contains pieces of information, so to speak. The range sum queries for I minus the least significant one of I plus 1 until I minus least significant 1 plus 2, and so on until I. So it stores this range for a particular subset. And then we can compute the range sum for any range using this data structure. And this data structure can also be extended to a d-dimensional so that we can actually deal with arbitrary number of dimensions. And then we get a computational complexity of 2 to the power of d times the d logarithm of n. So here are some just tips. I mean, it's actually fun to read the original paper by Fenwick. So it actually provides a very concise and good explanation of how this data structure works. I think the slides by Stephen Lim also makes a good job of doing that. And then what's kind of fascinating with this is that implementing these Fenwick trees is just a few lines of code, because you can get highly efficient and effective recursive implementation. So I truly recommend that you do this, and actually it's a very useful data structure which you can use in many different problems, including the next week's problem set. Of course, the third tip is to learn to use these trees, and they're also known as binary indexed tree because you find the particular value you're interested in by looking at the binary representation of these numbers. And then there is another data structure which is less useful than the Fenwick tree, but can also be quite useful. It's called the segment tree. So here the difference is that we're both interested in getting the sum of a range, but we also need to update ranges. So not only changing individual values, but updating a full range of elements at one time. So this is, for example, finding the minimum and maximum in ranges, and to find the sum of ranges can be used here. So again, it's an n log n to pre-compute, but here we need to have a slightly more kind of complex representation where we store these values in an ordered fashion so that we can find them easily again. And here are just the kind of definitions of how to compute a particular value from this linear data structure representation. So I recommend that you look up these data structures in the course book because it's much easier to read them, I think. And then here is just a summary. So to build a tree from an array, you can do the segment tree in linear time and the Fenwick tree in n log n time. So we can see here that if you have dynamic rmin rmax queries, so that means that you need to change things, then this is what segment trees are really good at. In both cases, we can do the range sum queries very well. And actually the query complexity and the point update complexity is the same. When it comes to implementation, the Fenwick tree is much simpler to implement than the segment tree. So to conclude this lecture, I want to say a few words about debugging. A general tip is that if you get stuck for too long, if you really have tried all the different things you can think of, then, or maybe you should not ask me, you should ask Herman, and he can provide a particular the particular test case where your data fails on. And where you really, the reason why we don't make the test data available is because two things. First of all, I think it's actually an important skill to be able to create your own test data. Secondly, it's also very good to try to figure out what could be wrong even without knowing the particular test case. Because of course this is often the case in real life. I mean, you might that you need to create your own test data if you want to be able to test your program. And then another general tip is that if you're really stuck, take a break or try another problem. So here is just a long list of different includes. So if you're using C++, it's good to basically include all the different basic libraries, including this bit vector, which is useful. Okay, so here's a summary of what I've been talking about today. First of all, learn to use basic data structures in standard libraries, such as vector, map, stack, queue, priority queue, and set. Also, unordered map is very useful because it's very efficient. You should use the union find data structure to represent collections of disjoint sets when you need to efficiently check memberships and merge sets. And as you will do in the exercise almost union find, you can also extend this to handle move and delete. If you need to compute range sum queries, So you need to sum up a sequence of values. So basically you have an array, and then you need to sum up a continuous subsequence of that array. That's a range sum query. If you need to do that, then the Fenwick tree is the perfect choice. At least, I mean, if you need to update the values. If you don't need to update the values, you can just pre-compute the range sum, and then you're done. But if you need to update it, then the Fenwick tree is what you need to use. And this can also be extended to higher dimensional data. If you also need to find a minimum or maximum, not only the sum, but you still need to make updates, then you should use a segment tree to solve this problem.